Let's do some examples now. What if we have an electric field that points to the right and has a magnitude of 2,000 newtons per coulomb, and we have a disk with a radius of 10 centimeters? What is the electric flux through the disk? Let's start by writing down our equation for electric flux. It's equal to E dotted with A, the scalar product between E and A, which means E times A times cosine of theta, where theta is the angle between E and A. At this point, we might like to draw our area vector. It's parallel to our normal vector. There's our area vector. Let's see what we have to fill in here. We'd like the magnitude of the area. The magnitude of the area is going to be pi times r squared. So it's pi times 0.10 meters squared. Our area is 0.0314 meters squared. Let's put our information now in. E means the magnitude of the electric field, 2,000 newtons per coulomb, times our area, 0.0314 meters squared, times the cosine of the angle between the two vectors. Our area vector points this way. Our electric field vector points this way. We see that the area between them is the given angle of 30 degrees. Pop all that in your calculator and you should get 54.4 newtons per coulomb times meters squared. Okay, there's the electric flux through that surface. A couple of comments we might make here is that this is a scalar quantity. This is really important. It's allowed to be positive or negative, but it can't have a direction, so no direction. Just like temperature is a scalar, and that's allowed to be positive or negative. If there's no direction, it means there's no I, J, or K in your answer. I know you've been doing physics for a while and you're probably pretty good with vectors, but it is easy to make a goof, so sometimes it's nice to have these reminders. Follow-up question in this problem is, what would be the flux if N is perpendicular to the electric field? So that question is asking, what if we take our disk and we rotate it so N is perpendicular, so N points straight up? I'm going to try and draw that in. So let's say we take our disk and we rotate it down here, which means our N points straight up, which means our area vector is straight up. That means that our angle between the area vector and the electric field vector is 90 degrees. Then our electric flux would be E times A times cosine of 90 degrees. Cosine of 90 is 0. That would give us 0 for the flux. What that means is that no electric field lines would cut through the surface. The last bit of this follow-up question is, what if the normal vector is parallel to the electric field vector? So now we take our disk and we rotate it up a bit so that the disk itself is perpendicular to the field and N is parallel. So I'll try and draw that guy. So if we rotate the disk up, now the disk looks like this. The N vector points out like this, which means that the area vector comes up like this. Now the angle between the area vector and the electric field is 0 degrees. Those guys are parallel. So then your net electric flux is E times A times cosine of 90 degrees, which would be E times A. So E was 2,000 newtons per coulomb. A was 0.0314 meters squared, times cosine of 90 is just equal to 1. That would give us a net electric flux of 62.8 newtons per coulomb times meters squared. Here's another example for you. I think I'll leave this one as a homework problem for you to give a try, and I'll post a solution for it. Just give you a little hint. Think super carefully about your angle. Is the given angle actually the angle you have to use in this problem? Here's another homework question for you to do. It's pretty much the same as the one we just did, except this time it's all words without the picture given. I'm not going to make a video for this one, but I will write up and post the solutions if you want to check your answers. This is another similar example, just given in a slightly different way. We have a 2 centimeter by 3 centimeter rectangle lying in the XY plane. So let's call 2 centimeters the length, 3 centimeters the width. So this is our length of 2 centimeters. And this is our width of 3 centimeters. And we'd like to find the electric flux if we know what the electric field is. So this is the same problem, but this time we're given everything in a vector format. So let's remember that electric flux is E dot A. So far we've always been doing the magnitude of E times the magnitude of A times the cosine of the angle between them, and that's valid. But the other way to calculate scalar product is you multiply the x components, you multiply the y components, and you multiply the z components, and you add all those guys up. Since we know the x and y and z components of electric field, Ex is the part that comes before I, that's 100 newtons per coulomb. Ey is the part that comes before J. Notice that there's no J here, so the y component must be 0. And Ez is the part that comes before K, that's minus 200. So we have those components. If we can sort out the components of the area vector, then we can go ahead and use this format to find our scalar product. So let's remember about area vector. The direction of the area vector is straight out of the face. So that comes up this way. There's the normal vector, and the area vector is parallel to that guy. Now I'm arbitrarily picking up as the direction of my area vector because it's not a closed surface. I can't tell if up or down is out, so I'm arbitrarily just going to choose up. So the direction of my area vector is straight up. I've got straight up labeled as the y direction, so I'm going to put in my area as a vector. So area is equal to length times width, and it's going to be in the j direction. So I've got 0.02 meters times 0.03 meters in the j direction, or 0.00, how many zeros? One more zero, I think. 0.6. Let me just double check, make sure I got the right number of zeros. Yeah, that's meters squared in the j direction. So for my components of my area vector, Ax equals 0 because there's no I hat part. Ay equals 0.0006 meters squared. Az, we see there's no k hat part, so Az is equal to 0. Okay, we're all set to calculate our flux. So our electric flux is Ex, that's 100, times Ax, that's 0, plus Ey, that's 0, times Ay, 0.0006, plus Ez, that's minus 200, times Az, that's 0. So our net electric flux in this case is 0. Okay, for part B, let's say if our electric field was 100I minus 200J, what would that give us for the electric flux? I'll post the answer, but I won't make a video. Let's build on that previous example a bit. We have an electric field. Notice it has an x component and a z component, and it's near a cube. So now rather than just a flat surface, we have a whole box. The linear dimension of the cube is 0.1 meters. That means it's 10 centimeters on this side, 10 centimeters on this side, 10 centimeters on this side. Determine the electric flux through the front face of the cube, or this yellow side right here. Okay, so if we're going to calculate the electric flux, let's remember our definition of electric flux. Electric flux is the scalar product between electric field and the area vectors. We can do magnitude of E times magnitude of A times the cosine of the angle. To me, finding the cosine of the angle feels a little bit dicey. I think I'd rather just go ahead and use the component method. Okay, this means I need to identify all of my components here. Let's start with the E components, the electric field components. So they're given. It says my electric field is 20,000 I plus 20,000 K. So EX, why don't I just write out my vector first? So 2 times 10 to the 4 I newtons per coulomb plus 2 times 10 to the 4 K newtons per coulomb. So I just applied my distributive property there and I wrote it out as a more familiar looking vector. My X component is the part in front of the I hat, and my Z component is the part in front of the K hat. There's no J hat here, so my Y component is 0. Let's write those guys down. EX equals 2 times 10 to the 4 newtons per coulomb. EY equals 0. EZ equals 2 times 10 to the 4 newtons per coulomb. Okay, what about my area vector? This time I have a closed surface, so the direction of the normal vector is straight out of the surface. For my front face, it comes facing out of the front like this. My area vector is parallel to that guy, so my area vector points straight out. So my area vector now is in the Z direction. So my area vector A is equal to the area of this face. So that's going to be length times width, A squared, in the Z direction, K. So 0.100 meters squared K hat equals 0.0100 meters squared K hat. That means now I have my X and Y components of the area vector. AX is 0, no X component. AY is 0, no Y component. AZ is 0.0100 meters squared. Okay, all set to pop my components into my expression now. EX is 2 times 10 to the 4 newtons per coulomb. AX is 0, plus EY, which is 0, times AY, which is also 0, plus EZ, which is 2 times 10 to the 4 newtons per coulomb, times AZ, which is 0.0100 meters squared. That gives us an answer of 200 newtons per coulomb times meters squared. Okay, things to comment about on our answer is it is a scalar quantity. That means that there is no direction. If there's no direction, there is no I, J, or K in the answer. That's really important. The positive value means that the electric field lines are coming out of the box. So if our electric flux is positive, the electric field lines come out. So if you're handy at drawing, you could draw these electric field vectors and you could see that they would come out through the face of that box. Now for a homework question, how about you find the flux through each of the other 5 faces? Add them all. Now then this is just thinking forward a little bit. Add up that total flux and ask, does that help you figure out anything about the charge in the box? That should help give you some insight when we get around to Gauss's law.